Hello interwebs, welcome to Let's Fix Computers. I've got a HP 15-EG series laptop here that doesn't power on. If we plug in a charger, then we get no light on the side. So, on the other side, let's just plug in that charger, plug that in, and the indicator light doesn't come on. Did I just see a white flash? Let me just check that again. No, that was nothing. So there's no charger light. Now, these symptoms are extremely typical around here. There is a good chance that this is just a power fault in the laptop. There's probably a dead capacitor in there or something like that causing a short on the main power rail, and we're going to find that capacitor and remove it, put a new one on, and the laptop will be A-OK. So this is going to be pretty typical. And I've got many videos demonstrating this repair, if it is what I think it is. But it's been a hot minute since I've really wound back and done a proper explanation of everything that's going on. So, explaining all the terminology that I go through, the whole works. So in this video, I'm going to aim to try and explain it in basic terms to help a beginner really grasp what's going on here, how we find the fault, and why the fault stops the laptop from working. So, bear with me, this one's probably going to be a long one because there's lots of waffling to do. And for the people who are just like, you're talking too much, get to the point, this isn't the video for you. If you want quick answers, then go and watch TikTok. This is long form content, kids. Let's go. So let's get the bottom cover off of the laptop. With no light, with no charge indicator light, this means one of two things. It means that there is an electrical fault in the laptop that is causing the EC, that's the embedded controller, to say, no, I detect a fault, we are not accepting power. You are not allowed to apply power to this laptop, and it switches off the DC input. It does this using the DC in MOSFETs, which we'll have a look at in a moment. The other possibility is that there is an actual fault with the EC or perhaps the PCH, which are the two very low-level chips that get to decide if the laptop will turn on or not. That's less common, and hopefully it's not that because that's also significantly harder to deal with. So what we're hoping for is just a common electrical fault that's caused the EC to say no, and all we need to do is find what that fault is, clear it, and then the EC will be satisfied and allow the laptop to turn on. So let's get this back cover off and then we'll take a closer look. With the cover off, the first thing I'm going to do is disconnect the battery. And while I'm taking out the battery, I'm just going to start looking around the board. I'm looking for any obvious signs of damage. Obvious damage that you can see with the naked eye from this distance is pretty uncommon. You're usually going to have to look a lot closer if you want to see any damage, if at all. But now and then you'll see something screamingly obvious. You'll see a burn mark on the circuit board or something like that. And if you do, then congratulations, because you've just found your problem. So I'm just having a look around while we take screws out. All right. So this laptop has a pretty typical layout for a modern laptop. Our CPU is here, and we've got a single heat pipe going to this cooling fan. In this area of the board, the laptop would have an optional graphics card. That's not present on this one. If there was the optional GPU fitted to the board here, where all these empty pads are, then you'd probably have an extra heat pipe or just a reinforced one, and that would go across, and there would probably be a two-fan system that would allow more airflow, and thus it can dissipate more heat to account for the extra GPU. But that's why we have these extra cutouts and stuff. It's pretty uncommon to find laptops with the dedicated graphics, though, in my experience. Many laptops have the provision for it. Very few of them ever actually have it fitted. So, as I mentioned, at first blush, I'm not seeing anything obvious. I think we'll go ahead and we'll take the motherboard out before we start taking any measurements. Sometimes when I'm usually in these videos, I'll take the back cover off and I'll do some initial measurements to see if I can take a guess at what the fault will be before I run the intro to the video. But really, if you're going to do anything at all, you're going to need to take the motherboard out. So yeah, we may as well just get on with that. I think I've got all the screws out the motherboard now, so I'm just going to start lifting it and just feel it out. Nope, I've missed one straight away. Never do anything sudden when disassembling a laptop. Never just assume you have all the screws and go wrench. Always just go as far as you think you need to and then just have a feel, see if anything is holding up, see if anything is snagging. That's snagging down there. How about now? Yeah, there we go. And now I've taken the motherboard out, I'm going to check the back plastics here as well, because if anything has overheated or gone bang, it will leave a black scorch mark on the plastic. That's a really easy way to spot faults early. This plastic looks pretty pristine, so nothing to see there. So as such, there's almost zero chance of seeing anything on the back of the board. And no. The board is technically double-sided, but there's very rarely anything significant on the back. We've actually got our audio chip down here, and it looks like we've got our CPU PWM chip up here. You know, that's an important chip, but not relevant to this particular video. We've got a couple of MOSFETs here that look very power related. You can tell because they've got big fat traces going to them. So that may well be important. And in fact, that goes up to here where the DC jack was plugging in. So that's actually our first DC in MOSFETs. So we'll talk more about those in just a moment. So let's start tracing the route that power is going to take through this motherboard. I'm going to start in the top left here. This is where the DC jack connects to the motherboard. I'm going to put my multimeter into resistance mode. So that's the ohm symbol there. You can just see at the bottom. And so what we're measuring here is the resistance between the probes. So if the probes touch, then there is functionally zero resistance between them. So we get a reading of 0, or in this case 0.1 whatever, you know, less than 1 ohm. Now, what we're looking for in the motherboard is a short circuit, or to be precise, a short to ground. That means we're looking for a place where a power rail has a direct path to ground, so positive and negative are connected together through a faulty component. That's what would cause this not to work. So to give an extremely basic example of this, the DC jack, our positive and negative, the positive and negative shouldn't be connected together. That's just a fundamental thing. They should not be connected together. So what we'll do is all the negative stuff will go to ground, and ground is going to be just any bare metal on this board, basically. So all of these screw holes, these are all ground. So I'll put my black probe on a ground by touching it against this screw hole, and I'll put my red probe against the positive connections of the DC jack. And as you can see there, we're getting a reading of about 650 kiloohms, so that's 0.56 megohms. So that's lots. That's high. That's very high resistance. Now, the exact number doesn't really matter. For this level of repair, we're looking for 0, basically. If it's not 0, we don't really care. Now, when you get into higher end repair and a bit more perceptive diagnostics, then you can pay attention to the number, and that might give you more information. Like, if the number seems lower than you're expecting, that might be a hint that you're close to the fault. You know, the fault is not on the area that you're measuring, but it's close by. It's downstream from here, you know. But for this level of repair, the only number we care about is basically 0. If it's not a 0, We don't care. So, our DC jack, that's fine. That's not shorted. Okay, cool, no problem. So, the next thing we get from the DC jack is this guy here. This is a TVS diode. That's transient voltage suppressor. What this is it's a diode which conducts power only in one direction. And this has been wired as such that it conducts from negative to positive. And that seems kind of strange because you think, well, that's not going to do anything because there's no power going from negative to positive, you know. For people who are talking about electron flow, bear with me here. We're going basics. And you'd be right. This thing doesn't do anything at all unless positive and negative are the wrong way around. So if someone connected up a third-party aftermarket charger to this that was wired incorrectly, this would conduct the power that's connected to the negative rail up to the positive. So it would basically bridge out the input, thus protecting the laptop from being wired in reverse. The other thing that it also protects against, and what TVS diodes are usually there to protect from, is although this won't conduct from positive to negative, diodes have what's called a breakdown voltage, which will be on this TVS diode, it will probably be like, I don't know, 30 volts, 50 volts, or something like that. And that's well above the 20 volt input for this laptop. So the idea is that if the voltage gets too high, if it's gone way above what the laptop is supposed to receive, this guy will break down and start bridging out the input again. So it's also protecting the laptop from over voltage. And that might be that, again, you've got a faulty charger that's sending too much power. Or it might be that you've got a static shock. You know, a big static shock has come down the line, and that static shock that might damage the laptop, again, will just get bridged out through that TVS diode. If this guy was faulty, then we would see a short circuit on the DC jack. Because we saw high resistance there, there's no problem, we move on. So, let's follow the path. Now, when we look closely at this section, you can see that this doesn't seem to go anywhere. It goes to a little row of dots there. Those are called vias. That's VIA. And the via is where the trace goes through the board. It goes via the board to the other side. So if we flip the board over, you can see that they're coming out there on this big fat trace that comes down the board into these guys. So these are DC-in MOSFETs. This is the first part where the power can actually be switched off by the laptop. So from this point on, I'm going to start bringing in the microscope so we can look closely at things. And I'll switch back and forth so you can get a big bird's eye view and a close-up view as and when we need it. So as I mentioned, here's where those vias come through from the other side of the board. And they're going up along here and into these DC-in MOSFETs. So a MOSFET is fundamentally a digital switch. When you apply a voltage to the gate, it will conduct power through the MOSFET. So it's a digital switch. And you can see that we've got our input here, our output here, and this guy is on its own. There's a separate wire going to there. So that's the gate that turns it on and off. These three and those four are connected together. So then we go out of that and directly into another one. These are usually found in pairs like this. And same deal, we've got our inputs there going to our outputs there, and there's a guy on its own there. That's the gate. So let's check if there's any problems around here. The first thing I want to know is, again, at the output from here, do we have a short to ground? So again, I'll put my black probe on a screw hole for ground, and I'm just going to check the back of here and just see if there's a problem there. Aha! All right, so look at that. We've got 0.3 ohms. So this is supposed to be at 20 volts when the laptop is running. So it shouldn't be connected to ground. So remember what I said, when we get 0 on the multimeter, that means that the probes are effectively connected together. So there is a connection from here directly to ground. If this is supposed to be at 20 volts, that's bad. That's a short circuit. So we've discovered a reason why the laptop doesn't turn on. The main power rail is shorted to ground. So the laptop is able to detect this short to ground because it's measuring current going through the main rail. And so when you plug in the power, it detects a sudden skyrocket in current, because when you have a short to ground, effectively infinite current will flow until the power supply can supply no more. So the laptop is detecting that sudden surge of current and going, that's a problem, cut the power. And it switches off the gates to these MOSFETs, preventing any more power from coming into the laptop. And it does this fast enough that we don't even see the LED, the charge LED come on. This happens in the blink of an eye kind of thing. So that's why the laptop appears to be dead, because these MOSFETs are getting shut off the instant that fault is detected. Now at this point, it's very tempting to start following the money through the board. This board is actually a great example of having big traces you can follow. You can see that our power trace goes all the way along and up and over, and it goes through the board, then comes back up and then goes down here and so on. And you could start following that trace if you want, but it's very easy to get lost doing that, because at any moment it could go to inner layers of the circuit board. And as soon as it does that, you're kind of going to lose track of it. So what we want to do at this point is we want to go directly to where we know the power is going to end up next. Now, this laptop is probably running what's called a narrow voltage DC power architecture. And that means that the DC input goes through another regulator, which brings it down to a voltage that's fairly close to what the battery is running at. And there's a couple of types of laptops that you'll typically see. One is narrow voltage DC like this. The other type of laptop, you will typically see the main power rail just runs at either charger voltage or battery voltage. And that means that the main power rail could be anywhere from 11 volts from the battery up to 20 volts from the charger, which is a pretty big swing. Narrow voltage DC, because the charger is being regulated somewhere else on the board, your actual power rail will end up being only a couple of volts wide. You know, it'll be, well, basically whatever the min and max of the battery is. So what we want to do is we want to find where that next point of regulation is. So usually the next time that power is going to get regulated is probably going to be somewhere near the battery connector, which is here. So we're going to have a closer look at this power area down here, the battery charger. And we're going to see what we can identify there. So here's our battery connector. And you can tell which ones are positive because these pins go up to a big fat trace going into a MOSFET. So that's going to be our positive pins carrying power. So they're going through this MOSFET. And then we go through this bit here. Now, this here is a current sense resistor. You can spot them because it's generally just sort of a big black flat package like this. It will probably have, like, in this case, R005. And what you do with these is you have your power going through this resistor, and if you notice, there's two little dots there and there. So those are vias. There's two wires going to each end of the resistor, and those go back to the power regulator on the board, and it's measuring a tiny drop in voltage between one side of this and the other. So because there is a slight amount of resistance through that resistor, the voltage will drop a little bit because there is resistance. And by measuring that drop in voltage, you can calculate the current going through the resistor. So basically, by using this current sense resistor, you can measure how much power is going in or out of the battery, which is how the laptop can measure power draw. And so likewise, there's going to be another one of these somewhere else for that DC rail we found that was shorted. So we go through this current sense resistor and we become this big fat trace here, which is going places. So this is most likely our main power rail because it's directly driven from the battery voltage. And by opening and closing this MOSFET, you can allow the battery to charge or you can allow the battery to discharge into the rail. So let's see if this is shorted. So once again, I'll put my black probe on a screw hole as a ground, and we'll just check this current sense resistor here. So the meter's taking a moment to settle, but it looks like we've got about 19 kilo ohms there. So that's 19,000 ohms. It's high resistance. So remember, we're looking for 0. When we measured the DC in MOSFETs, the output from the DC in MOSFETs was 0 ohms. So again, we don't particularly care what the number of this actually is because it's not 0. So this main power rail isn't actually shorted. Now that's very interesting because we've now narrowed down our culprit significantly. If you look at this handy dandy diagram that I'll now put on screen, which Editor Me now has to make because I've deemed it so, we've now narrowed down the possible space where our fault could be. We're somewhere between the DC in MOSFETs and the main rail regulator. So we need to find out where the connection between the main rail and the DC in rail is. So following this back a little bit further, we've got more MOSFETs and inductors here. So this is probably that regulator. So it's a little bit tricky to see at face value exactly how this is all hooked up. But if we pretend that we've got a path through this area somehow, it's going through these MOSFETs and inductor by some path. These are connected together somehow. And if we come up here, you can see we've got another resistor here. That's another current sense resistor. And again, you can see 2 little lines coming from there, going back to this chip here. So this is our regulator chip, and it's watching the current going through this resistor. So this is this is a significant power resistor here. So if we go through there, we've got a cluster of vias there. Let's just see what's on the other side of those. And wouldn't you know it, it comes up there right next to our shorted MOSFET. So here's where the power is coming out of the MOSFET. It goes straight through the board. It comes up there and goes through this current sense resistor and then gets regulated into our main power rail. So at this point, our fault exists somewhere between here and here. But also let's remember, this trace goes off somewhere as well. Let's just come back to the wide view. So remember, this trace is also going all the way over here. It goes down there, it goes through the board, across a bit, then it comes back up and comes up to all the way up here. So it's going to other places. So why is it going over here? Well, the reason why it's coming all the way up through here is it ends up in this area here. And if we flip the board over, that's coming up on our Type-C port here. So this is a Thunderbolt port, and if you remember, a lot of modern laptops can be charged through the Thunderbolt port, or USB, or just a Type-C port, as I'll call it. Because it might, if it's an AMD laptop, it won't technically be Thunderbolt. So this port also has some power regulators on it that allow it to charge to power the laptop. So we've got to remember as well that because this region here is also connected to that shorted rail, we might have a problem up here as well. So this whole area up here is also suspect. But we'll come back to that in a minute. Let's go back to this area down here. Now, the absolute #1 classic reason why you might have a short to ground is because a small capacitor has failed, and it has failed short, which means instead of being a capacitor with 2 plates like this, the plates have shorted together like this, and it's turned into a wire. And the capacitors on the board take 2 major forms. Well, 3 technically, but there's 2 on this board. These brown packages here, these are MLCC, multi-layer ceramic capacitors. These are the guys that fail all the time. So those are primary suspects. The other type of capacitor that we see, if we come up here, are guys like this. This is a tantalum capacitor. So again, this is also a capacitor, but it differs slightly because it's generally, tantalum capacitors are much bigger packages. They have a much higher capacitance rating, and they're polarized, which means it has a positive and a negative connection. You can see there's another one there with its positive and negative end. So these guys are typically low voltage, high capacity, whereas MLCCs tend to be high voltage, low capacity. I won't drill into all the reasons or all the functions of the capacitors in this video. It's outside the scope of it. But that's how we're recognizing the two major types. As a side note, the third type of capacitor that you may see is this guy. This is an electrolytic capacitor. It's a big can. You generally don't see these on modern computers anymore. These guys can be high capacity and fairly high voltage, but they're huge. So very unpopular in modern laptops because they're just simply too big. But at any rate, these big cans, those are the traditional capacitor shape. When someone says capacitor, that's the kind of thing you think of. So above all, these multi-layer ceramic capacitors, these are the kind of guys that tend to fail all the time. Because they're literally ceramic, heat cycles, the board flexing because the laptop's getting beaten about and stuff like that, they can cause these capacitors to crack. And what you have inside is a standard capacitor is just 2 plates of metal. But a multi-layer ceramic capacitor, in order to have a high capacitance, they have the 2 sides are lots of plates. So there are lots of plates in a pattern like that, all going between each other, but not touching. But if it cracks, the plates could touch like that. So these 2 plates, these aren't touching, but these ones, these are touching. That's how you get a short through your ceramic capacitor. So that means that these guys around here, remember, we're shorted on this area going up to the DC MOSFETs. All of these guys are prime suspects to be faulty. But the question is, which one? So how do we know? All right, so the first thing we can do is just a visual inspection. At this point, we've narrowed the scope of where the fault could be on this whole motherboard down to this cluster up here or this cluster here. The only other option is that there is a fault with these MOSFETs themselves, but we'll get to that in a moment. So because we've eliminated basically all of this as a possibility, we've got a much smaller area that we actually have to inspect. Based on what we've discovered, it's not going to be any of this at all, because our main rail isn't shorted. So we can just ignore all of this now and start paying attention to just the areas we've identified. So let's take a real close look at some of these capacitors. I'm going to tilt the board up so I can see the sides of them and just refocus. And we're just going to check if any of them have anything unusual about them. We're looking for cracks, spots, that kind of thing. Those look really clean to me, which doesn't mean that they're not faulty, but it does mean that there's nothing to see visually. Yeah, those look fine. Nothing going on there. Going up to that Type-C port here, these 2 MOSFETs, those are going to be handling the power coming in through the Type-C jack. And that's going to be managed by probably this chip here, would be my guess, maybe. But there's not really any cluster of capacitors around here. That's just passing the power on, and it's relying on the power regulators downstream to do filtering with capacitors and stuff like that. So really, unless something up here has gone spectacularly wrong, there's not really a lot to see here. So, you know, I don't really suspect anything there yet. So we'll ignore this for now. So this area visually looks fine. And back on our DC input jacks here, there aren't any capacitors around here that could be shorted. But what if it's these guys themselves? So firstly, remember what we said. We have a short to ground. So our faulty component is pulling the rail directly down to ground. Now think about what these guys are doing. We've got power going through this MOSFET to here, and then it goes through this MOSFET to here. So we've got our power flows going along like this. There isn't a path to ground here. These MOSFETs don't connect to ground. So you can have faults with these MOSFETs, but these MOSFETs, even if this guy had gone nuclear and shorted out, it doesn't connect to ground. So at this point, there's no reason to believe that there's a problem with it. Now, we can actually check if it's functioning as normal, so let's do that now, just out of interest. I'll set my multimeter to diode mode, so we're on the resistance selector here, and if I push the mode button, we get a diode symbol up the top here. So now we're in diode mode, and what I'm going to do is I'm going to check each side of the MOSFET. So let's start here and here. And in one direction, we'll find that it passes no current at all. So just over limit, which means I cannot measure this. And if we measure it the other way around, we see 0.55. And what that means is a 0.5 volt drop from one probe to the other. And that's the kind of voltage drop you see through a diode. And the way a MOSFET works is that in one direction, from one direction to the other, it behaves a lot like a diode. And that's what we're seeing here. So with my red probe on the left, we're seeing a diode drop of 0.5 volt from red to black. And in the other direction, because it's behaving like a diode, it's just blocking everything. So we get over limit in one direction and 0.5 in the other. That's how we are expecting the MOSFET to behave. So let's check the other one. So here, over limit, and the other direction. And once again, there's 0.5 volt drop. So both of these are behaving as normal. If they were faulty, in one direction or the other, we would see a 0 volt drop. And that would mean that power can flow directly through the MOSFET unimpeded. So it means that it's no longer capable of actually switching the power. But again, this doesn't allow that power to go to ground. It would mean that they're not doing their job, but it doesn't mean that the power goes to ground. So again, these can't be the fault. So we find ourselves at an impasse here. We know that something in this area is probably shorted, but we can't find it visually. We haven't seen any visible signs of failure. And we haven't measured anything else that's gone wrong either. So this is the point where most technicians will immediately say, inject power, also known as voltage injection or current injection. People can argue what to call it, whatever. I just call it power injection because it doesn't matter. So what do I mean by that? So if we pretend that one of these capacitors has failed short, that means we have a direct path to ground through our failed component. Now, if we connect power directly to the shorted component, it's going to conduct it directly to ground. And there's no limit on how much it can conduct at this point because it's just a wire. It has failed, and there is an unregulated path through it. So if you start passing multiple amps through this tiny failed component, it's going to heat up or even burn out. And you might ask, well, why hasn't it done that already then? Well, it hasn't done that because the laptop has detected the fault and cut the power before that can occur. But if we connected power directly into the rail in a manner that the regulator cannot control, then we can force power to flow into that rail and it will go through the shorted component and heat it up. Then all we have to do is find the hot spot. This is how power injection works. And by looking for the hotspot, that will reveal the fault on the board to us. Now, there are considerations that we have to think about when doing this. Because if we're going to inject power into the motherboard that the motherboard is unable to control, then we have to consider if that power could go anywhere or damage something. Because already we're bypassing the laptop's first safety mechanism, which is those DC-in MOSFETs. They're there to protect the motherboard, and we're bypassing that safety feature of the board. So before we inject power, we have to know where that power could be going and if we might damage something. Now, this particular instance is really cut and dry. Our main concern would be if we are injecting onto the main power rail or a secondary power rail in the laptop, because if we inject onto the main power rail, then that could be going up to the CPU, it would be going to the secondary power regulators, which in turn could be going to the memory, it could be going to the PCH, it could be going to the CPU, it could be going to other important things that might damage them if you just blast power into that rail. However, our main power rail isn't shorted. So we know that if we inject onto our shorted area, it's not going to get that far because this regulator here is blocking everything going through it right now. So we actually can skip all of our concerns here. The time where we'd really be worried about damaging the board is if we had a shorted main rail. The main rail is going to appear up here, where it provides power through these regulators into the CPU. And if we had a faulty CPU regulator, any power that we inject into the main rail could go directly into the CPU, and that would also damage it. Now, the reality is, if that happens, the CPU is probably already dead. However, that's not the point. You still be careful anyway, because, you know, once in a blue moon, you will get a CPU that will actually survive a busted regulator. But that's a topic for another day. So at this point, we've determined that our fault is somewhere on the DC-in rail, and it's pretty isolated to that area. So if we inject power here, we're fairly confident that we're not going to send that power to anywhere that we don't want it to go. So let's set up for injection. So to inject power onto this board, I'm going to use a DC bench power supply, like this one here. So a DC bench power supply, it can supply a fixed voltage and amperage based on my spec. So I can set the voltage, I can set the amps, so it will provide whatever I tell it to provide. And these bench power supplies are designed to work under any conditions. So if it's in a dead short circuit, it's fine with that. It will supply up to the amps that I have set. By comparison, if we have something like your phone charge or a typical phone charger that's like, I don't know, like 5 volt 2 amps or something like that. Firstly, we can't control the voltage out of that without additional stages. And 5 volts is a bit too much for injection, which I'll discuss in a moment. And also, if we put that into a dead short circuit, that's liable to damage the power supply because it's expecting to deliver up to, say, 2 amps, but it's not designed to work beyond 2 amps. It's not designed to be in a situation where it's being asked to supply infinite current into a short circuit. So this is where a DC bench power supply comes in handy. Now the reason why we inject at 1 volt is because that's a very safe voltage. No matter where that goes, there's almost nothing on this board that is going to be damaged by a volt of power being pushed into it. And this is important because even if you apply voltage to something that is not expecting it, everything has a breakdown voltage. Everything has a breakdown voltage. And what breakdown voltage means is that if you supply to something that is not wanting to receive power, eventually your voltage is going to be high enough that it will just smash that open and the power will be forced through. It's a lot like a dam trying to hold up water. The dam can only hold up so much water before it is overwhelmed. And that is breakdown. And at that point, the current starts flowing into the device when the device is not wanting it. And yeah, you get problems. So 1 volt is nice and safe. It's not going to damage anything. The amperage that we set is as much as we need to generate some heat. Now, for modern power injection, we use thermal cameras. And thermal cameras are really sensitive and will light up at something will light up when it's got like 2 amps going through it. So I usually inject at about 3 amps because that's going to make it nice and easy. You know, there's going to be no mistakes when we spot it. It'll be a glowing orange dot somewhere. If you don't have a thermal camera and you need to use other methods such as, freeze spray or just touching the board with your hands and such like, you might need to push up to 4 amps to make the heat noticeable enough. But for this demonstration, we're going to use a thermal camera. So my one here, this is an Infrared P2 Pro thermal camera. And as you can see, this plugs into just any smartphone. So I'm going to hold it, that way around, I think, just so you guys can see what's going on at the time. Yep. So I'm going to connect the power supply with a ground connection, and then I'm going to touch the board with a probe where I want the power to go. So what's going to happen is we've got 1 volt of potential difference across these. So a voltage is a potential difference, that it's how much potential power is between the 2 points. Now, because we have a dead short circuit on this board, when we touch the probe to the board, we'll have effectively the black on a ground and the positive probe touching an area that is shorted directly to ground. So through the board, the probes will be touching. What this means is that the voltage will go down, and what will happen is something like this. If I switch on the power supply, so at the moment the power supply is showing 1 volt and 0 amps. There's 1 volt of potential difference there, and no current is flowing because it's not connected to anything. If I touch these together, the power supply drops into a short circuit. So we're supplying 3 amps of current at half a volt. Now, the reason why we're at half a volt is everything has some resistance. There's resistance in the wires. There's resistance in this connection here where it's just the clamp. And if I move that, you can see that the voltage goes up and down a little bit where the quality of the connection is changing and so on. But the point is the voltage goes down. This is normal. This is what we're expecting. And if anything, we like it when the voltage goes down because the lower the voltage is, the less resistance there is, and that's the more current that is flowing into our faulty component to reveal itself to us. So that's what we're expecting to see. So I'll connect my black crocodile clip to a screw hole as a ground point. It doesn't matter where because all the grounds are connected together. So I'll just clamp that onto that screw hole there because that's a nice accessible one. We want to get a nice good connection there. In the old days, we used to solder jumper wires onto the board to make sure we got a really good connection, but that's kind of out of vogue these days, and with thermal cameras, it's just not necessary. So now I'm going to hold the thermal camera up, and I'm going to touch the current sense resistor that we were looking at, because we know that that is shorted to ground. So that will inject our power onto the shorted rail. So let's touch that there, and we're going to look for something that lights up. Here we go. And there it is. Can you see that big orange dot that's just flared up? That's what we're looking for. When I let go, the heat fades away again and it dissipates through the board. And then if I touch that again, and our heat source comes back, nice and strong. So we've discovered our fault. So let's go in for a closer look at that, and I'll give you a close-up with the macro lens so you can see exactly what's happening here. So here's the thermal camera with the macro lens on, and we're looking at that regulator where our DC rail becomes the main power rail through the laptop. So this point here, this is our current sense resistor, and then we're going through the MOSFET, the inductor, another MOSFET, and we come out as the main power rail. So this area is shorted, this area is not shorted. So once again, I'm going to apply power to the current sense resistor, and let's see which bit gets hot. And as you can see, that capacitor there is lighting up. So that guy is lighting up real hot. Let's see if I can get a temperature on that. So that guy's going up to about sort of 46, 47 degrees centigrade, which isn't turbo hot. Is that hot enough to burn my hand? I can just about feel that with my finger, but it's pretty vague. And this is the power of thermal cameras. You can see that our power supply is, because we're just touching a probe against a resistor, we don't have a very good connection here. So we're only actually getting about 1.7 amps into this connection. This is why using a probe isn't always the best, because I'm struggling to get a good enough connection into our short circuit. But again, with a thermal camera, no problem at all. So this was our guy that was lighting up there. And you can see under the microscope that, as when we inspected these capacitors earlier on, it doesn't look failed. Sometimes when you actually spot the capacitor, or when the culprit has been revealed to you, you'll go, oh yeah, look, there is a crack in that one. Or, you know, if we found it at the right angle, maybe we would see something. sometimes when you've injected power on it, by the time you've dumped 3 or 4 amps into a capacitor, it will definitely be cracked. And then you'll be like, oh, how didn't I see it? Well, you didn't see it because it wasn't cracked until you dumped 3 amps into it. So, however, this one is showing no visible signs of failure, but we know that's the guy because that's the one that's conducting all of the power when we send power into this rail. So let's remove this from the board, and we should find that our short circuit disappears. So we can use a hot air station to remove capacitors like this from the board, or my weapon of choice as of late has been to use hot tweezers. I've got these Secure HT140 hot tweezers here that I've been practicing with, and I find that they're a bit less dramatic than hot air. And for simple capacitor removal, they're my current favourite weapon. So I'm going to turn the board around to give myself a bit easier access. And that will allow me to come in like that with the hot tweezers. Now I'm going to take off both of these capacitors because I want to check what the rating on the other one is, because there's a good chance that these are all the same rating, these capacitors. Broadly speaking, they nearly always are. This one will be different because it's visually different, but all these ones that literally look identical, they're going to be the same rating. And I'm guessing it now, it's going to be 10 microfarads, I think, because it's always 10. So I'm going to use just one of the tweezers just to wet these joins a little bit. Just get some fresh solder on there just to loosen that up. There we go. And now we'll just come in and pinch that off. There we go. That's one. There we go. Let's take some measurements now. So once again, I'll put my multimeter back into resistance mode. So we're going up to the ohms rating. And we're going to check our rail again. And what we'll find is that we should no longer be shorted. So my black probe is on a screw hole. And let's just check the current sense resistor up in the top right here, where we've been previously checking. And now, instead of reading 0 ohms, it's now reading 130 kilo ohms-ish. So hundreds of thousands of ohms. So that's now gone high resistance. So our short circuit has gone. This means this laptop will technically work now. We've removed the faulty component. But we want to replace that, and I'll talk a bit more about that in a moment. But first, let's take a look at the capacitors that we actually took off the board. So let's just bring these guys back up. So let's just check which one of them was the faulty one. So hopefully without flinging them into oblivion, we'll just measure them. So that one is dead short. So that's our faulty one, because there's 0 resistance going through that capacitor, so it's dead. And if we measure the other one, I should put this down on some masking tape or something. And this one, as you can see, it's tough to get a read on these, but it's extremely high resistance because it's fully charged. Good. So I want to know what rating this capacitor is. So I'm actually going to stick it down, because I've nearly lost it twice now. So now I'll move my multimeter into the capacitance mode. So there's a little capacitor symbol there. And now we're measuring farads. So at the moment we're seeing nanofarad range. And if we just probe that capacitor again. I'm wrong. It's a 20 microfarad capacitor. So as you can see, we're getting 21 UF. That's microfarad. All right. And the size of this capacitor should be 0804. So if we just measure the size of the capacitor there, preferably without the solder blobs included. There we go. As you can see, that is 0.008 of an inch long. So that's how we know it's an 0804. You can buy little guides that make this easier, or after a while you just get a feel for it where you just look at it and you just know by sight, you can just guess it by sight. I have to set my calipers back to millimeters now, to like a sensible person would measure in. There is a metric scale for SMD components, but no one uses it, so... So, we need to put our capacitors back on the board. We've got a working one here, and I'm going to go into my stash. There we go, and I've got some 22 microfarad caps here. The capacitors do have a voltage rating as well. These 0804 capacitors in sort of 10 and 20 microfarads, they're probably rated for about 25 volts or so. And remember, this is a 20 volt rail because we've got 19.5 volts coming in from the charger. So that's the rating that they should be. If you're really unlucky, you'll sometimes see really exotic stuff like 06, 03 10 or 20 mic ones, and that's where you've got to watch out because a lot of the cheap capacitors might not be rated for 20 volts in that size. But at 0803, if you buy some 20 mic capacitors, they're probably going to be rated for 25-ish volts, around that kind of area. So you can buy these cheap on eBay, or you can buy them from an electronic supplier of your choice, like Mouser, DigiKey, etc. So I will grab a new one out this packet, and we'll swing the microscope in, and we'll put these two caps on the board. I'll add some flux just so we get some nice clean solder joins when putting stuff back on the board. That's way too much flux, but that's alright. And let's bring in our two capacitors. That's good enough. Now I'll just spray some alcohol on to clean up. There we go. There's a little bit of flux residue between those, but that's okay. And now just for posterity, let's go all the way back to those DC-in MOSFETs, and we can just confirm that they're not shorted anymore. And we've no reason to believe they will be, but just to show that we've actually solved the problem, I'll put my black probe on ground again, and if I touch this point, and as you can see, we're no longer shorted. So our fault is resolved, and we've replaced the damaged part. So I've put the motherboard back in the laptop now, and we're ready to actually test that it works. So if you remember back at the start, when I plugged the charger into the DC jack, there was no indicator light at all. So let's try plugging that in again and see what happens. So if we plug that in there, there we go. There's a little orange light there. It's kind of dim under the studio lights, but it's on. It lives. So I'll put the back cover on now, and then we can switch it on and just make sure the laptop starts and runs. So what was that capacitor that we replaced? So that was a bypass capacitor. And laptops have lots, well, all electronics have lots of bypass capacitors in. And they serve sort of, there's two main roles that they serve. The first one is to provide, well, there's kind of three roles, I guess. So the first is to provide a reservoir of power that might be near a controller chip or a chip that's doing work. And that's, the job there is to provide a small battery. So when that chip suddenly does something and takes a gulp of power, there is a small reservoir right next to it for it to take power from while the power rail catches up. Think of it like a stream flowing into... Think of it as a stream flowing up to a water wheel. You have a bit of an open space of water in front of the water wheel as a reservoir, and the stream is constantly topping up that reservoir. And so then every time the water wheel comes down and scoops a load of water through, there's a volume of water already there. And the stream keeps that reservoir topped up. So the next thing, which is what this one probably would be, is power smoothing. If you've got power coming in from an external source, you don't trust that source. You know, you don't. That power might be noisy and lumpy, and it might be from some crappy charger, or it might be from a charger where, you know, the big long length of wire is coiled up and wrapped around an AC cord that's putting loads of switching noise onto it and stuff like that. So the power there is the capacitor there is to smooth out the voltage on that line and just smooth out any lumps and bumps that are in the voltage. And then the third job is noise suppression. Modern electronics use what are called switching regulators, and that's what the MOSFETs are doing. They're switching the power on and off at high speed. And when you do that, it adds high frequency noise on the line. And that noise can get into the kilohertz. It can get into radio frequencies. And if you've got a switching regulator generating high frequency noise, and then a long length of wire of your power rail going across a board, suddenly that wire becomes an antenna and radiates that switching noise. And that's how you get electromagnetic interference, EMI. And based on rules, like on the back here, we'll find an FCC logo somewhere. It'll be in here somewhere. Well, here's European regulations, because this is the EU spec, and so on. And the rules of that is that the device isn't allowed to transmit any frequencies of that nature. The Wi-Fi card is, but that has separate regulations. The board isn't allowed to just generate noise, because otherwise you might put it next to medical equipment and it could interfere with the medical equipment, you know. So those capacitors are there to filter out the high frequency noise being generated from switching regulators. Now, the laptop will work without them, and there is an overkill number of them there. So you could probably take out a lot of those capacitors and the laptop would be just fine. But you never know what's actually needed and what isn't. And so best practice is always to replace it. I'm going to give up and just unwrap my charger. There we go. So best practice is always to replace the part that you removed. And it might be that it needs it, it might be it doesn't need it. You may know for a fact that it doesn't need it. But also, if you get into the practice of replacing parts, when the time comes that you're having to replace a part that is mission critical, that the laptop cannot do without, you'll be practiced at doing that. You'll know exactly how to approach that. But if you go through your entire learning phase just ripping parts off of the board without replacing them, the time when it matters, you're going to be like, well, I don't know where to find that replacement capacitor or how to measure its rating, and I don't have any spares. And you'll be stuck. So if you practice replacing the parts you remove, you'll be prepared for when it does matter. So there's our laptop. Let's push the power button. We've got a power light there that you can't see, but in a minute we should find we get a HP logo. Because we've had the battery out of this, it's going to take a while to come on. It's going to go through what's called RAM training. And RAM training means the BIOS is checking the memory and it's checking how fast the memory can operate. So it's probably going to turn on and off a couple of times as it tests different speeds until it figures out what the memory is ready to operate at. And then it will set those settings and actually start up. There we go. So that wasn't too long. Sometimes this can take like a minute or like 4 reboots. CMOS checksum is invalid. Yeah, that's because we took the battery out. There we go, folks. That's a fixed laptop. So thanks for tuning in. I hope you guys enjoyed that. And let me know in the comments if you like these more longer explanations, because as I say, in more recent videos, I'd probably go faster through that because it makes me look clever. But I think sometimes what makes a person look even cleverer is when they can explain it in detail to a layperson and help someone actually understand what's going on in these repair jobs. Good. Thank you as always to my patrons, my channel members, and my Twitch subscribers, and I'll see you guys next time. Bye.